Okay, so hello everyone and welcome to today's talk. Today Nancy's going to be talking about isoperimetric inequalities, and as usual we have the apéro after the talk at G69.
So hello everyone, welcome to my talk about isoperimetric inequalities. And first of all, I would like to thank the organizer, Sid and Johan, who is not here, for having me here, and also my professor, Professor Dalio, who assisted me throughout my thesis. So thank you, and let's get started. So first of all, an outline. So first of all, I would like to start with a little motivation, what it is about, and afterwards we will have a focus today on isoperimetric inequalities in the two-dimensional case and the n-dimensional case. And we will try to understand the proof outline, how we're gonna prove that, little puzzles, how we can build it together to see how that works. And afterwards, at the end, also a little application of isoperimetric inequalities in terms of geometry and analysis. So first of all, let's have a look at these patterns. Assume they have all the same perimeter. And now the question coming up is, what about the area? Which figure maximizes the enclosing area? And it's pretty actually intuitive. The answer would be the circle among all of them. And this is a little illustration for our two-dimensional case. Let's have a look how it looks like in a three-dimensional case as a little motivation to start with. So have a look in mathematical physics, a really intuitive or a really fundamental question is, why is the Earth, the planets, or the stars roughly a sphere? So the notation that the physical shape of the universe may be related to isoperimetric inequalities goes back to Ptolemy. I hope I spell it correctly. And actually, the first attempt was due to Poincaré. And he claimed that for a non-rotating homogeneous fluid mass, which is acted upon by internal focus of gravitation, the only figure which has the stable equilibrium should be a sphere. And so the idea behind that, how he tried to show that, was that the idea is that any equilibrium figure must have minimum electrostatic capacity among all of the equal volume. So how do we show that? And Poincaré used, of course, our isoperimetric inequalities to show that the sphere is exactly this figure, which minimizes our electrostatic capacity. So now, first of all, let's have a look at the statement for the Euclidean two-dimensional space, which says, let C be a bounded domain in the plane with a boundary gamma, which is a Jordan curve, which means nothing else that the plane is simply a simple closed curve. And in the Euclidean plane R2, and assume that gamma is absolutely continuous. Then it holds that L squared is bigger or equal to 4 pi times A. And L here denotes actually the length of our C, and A the area. So let's have a look at this figure here. So the L would be actually just the boundary, and the A would be the whole area interior to our C. And additionally, the inequality becomes an equality if and only if C is a circle. So this is exactly what we've seen before with the figures, now in a really mathematical formally described way. So how can we prove that? So let's start actually with the little puzzles we need for the proof. So I'm sure all of you have seen that already in analysis 1 and 2, which is the Gauss-Green formula, or it's also known as the divergence theorem. What we see here is let R be contained in R squared, be a compact area with smooth boundaries, and let F, which goes from S to R squared, be a continuously differentiable vector field defined on an open set S, which is contained in our R. Then it holds that the integral over our area R time with the divergence of f dx is exactly equal as if we would integrate it over our boundary of R of our vector of our differential vector field times our normal vector n dn. So how can we understand that? So as we can see in the picture, so this is actually our C, which is actually our delta, the boundary of our R, and it's actually equal if we integrate it over our normal vectors, or if we would integrate everything with the flux through the whole area. So it's actually like we are having a double integral here, which is a sum of all little pieces. This is exactly equal to if we would take the boundary and integrate it just over all the known vectors. Okay? So the next thing is our Wirtinger inequality. And what we're having here is for U be an element of C1, and with U of A, right? With U of A is equal to U of B, which is equal to 0, and the integral over A to B of ut dt is equal to 0. This is our condition we will need to apply our Wirtinger inequality. And then the following inequality holds. So what we have here is the integral over u squared of t dt is smaller or equal to b minus a squared. So I hope it works now. Perfect. But we are skipping some steps. Let me check. So we're here. So sorry for the interruption. What we have here is just an inequality where we have from the integral ab of u squared t dt is smaller or equal to b minus a squared over 4 pi squared of our integral ab of u prime of t dt. And the equality takes place in such that this inequality if and only if our ut is equal to a times the sine of 2 pi of t minus a over b minus a plus b times cosine of 2 pi t minus a over b minus a, where a and b are just some constants. So for those of you who've already had methods of mathematical physics, this is actually, we can think it as the eigenvalue problem. So these two are actually our conditions. So this is actually the normal one. And what we have here is just an extra constraint with respect to our inequality such that it holds. And this is actually the solution for our eigenvalue problem. So this is another way how we can interpret this inequality. And this is actually already those two main ingredients we need for the proof of the two-dimensional space. So what do we have here? So first of all, the proof idea, I would like to introduce this in 3 steps. So the first step is, so by Gauss-Green formula, given any point of x0, y0, what we get is that our A, the area, is equal to our integral over our boundary gamma of minus y dx plus x dy. Applying our divergent theorem, what we get is this is exactly equal to our integral over gamma of y0 minus y dx plus x minus x0 dy. And it's important that our boundary gamma of C is counterclockwise oriented. So, and now we are trying to consider parametrization of gamma. So I believe you have seen that also in analysis, the parametrization. In this case, it's actually a simple parametrization we're doing, where S is the arc length. So we can see here in our graphic, suppose this is actually our figure we're having. And through the parametrization, we're trying to have a look at it on a circle, such that we can show the inequality. And therefore, what we have here is x prime squared plus y prime squared is equal to 1. And by applying Cauchy-Schwarz inequality, and I've left out a few steps here, what we have would be, so A, we would first of all plug in our parametrization such that we have the whole integral between 0 and L. This is where the 0 and L comes from. And applying afterwards the Cauchy-Schwarz, we will get the square root, which is here over 1/2. So the whole thing is smaller or equal to the square root of L over 2 of the integral between 0 and L of y0 minus ys squared plus xs minus x0 squared ds. And now let's have a look at how we can apply those y0 and x0 such that a little trick here. So what we're doing is we're having a look at our x0 and y0 as the barycenter of gamma. So we're looking at exactly in the center of our figure. So what we have is afterwards we will have the following properties. x0 minus x0, so x at point 0 minus x0 is equal to x at point L minus x0. And exactly here also the integral from 0 to L of xs minus x0 ds, which is equal to 0. And exactly the same here for our y's. And now this seems maybe familiar for you. This is exactly the condition we need to apply our Wirtinger inequality. So the little trick here is we are trying to have a look at it in the barycenter such that we can apply our Wirtinger inequality to simplify the whole thing. So what we have here is, this is exactly the formula we get before for our A with Cauchy-Schwarz inequality. And this is smaller or equal to L squared over 4 pi squared of our integral between 0 and L of x prime squared plus y prime squared ds, which is equal to L over 3 in power of 3 over 4 pi squared. And this inequality is exactly if we apply the Wirtinger inequality here, with our A is equal to 0 and B is equal to L. So if we rearrange everything we've had before, together we will get that A is exactly smaller or equal to the square root of L over 2, which we've had before, of L over in power of 3 over 4 pi squared in square root. Calculate together, this leads exactly to our inequality, which is L squared over 4 pi. So by rearranging, we get exactly that L squared is bigger or equal to A times 4 pi. Exactly what we want. So now we've proved the inequality. So the last step remains. What we have to show is the equality, when that holds. So here, the question coming up, when does actually the equality holds? So previously thoughts about Wirtinger inequality tells us that the equality holds if x at point S is equal to x0 plus L over 2 pi of cosine of 2 pi over Ls plus phi. So we've seen that actually before in our Wirtinger inequality. We have an inequality, and afterwards the equality holds if and only if u of s is equal to a term. This is exactly these two terms which we can conclude from our Wirtinger inequality. And here I've left out some calculation steps which we would use. But here, the most important is the inclusion equality in isoperimetric inequality holds if and only if C is the circle cos of those two terms. So to sum up with, in our two-dimensional space, it's quite a simple version. So the only thing we need is only the Wirtinger inequality and the divergence theorem. Pretty easy, but let's have a look at the n-dimensional space. That's gonna be a little bit different, so we will have to deal with different things as here. So let's have a look at the statement first. So for the n-dimensional space, the statement is more or less exactly the idea as the idea in the Euclidean plane. But here what we have is let G be a measurable set in Rn with a finite measure. Then our perimeter of G is bigger or equal to n times omega n over in power of 1 over n of our measure of G in power of n minus 1 over n. So this is nothing else as we've seen before, but for n-dimensional way. What we have here is omega n is exactly equal to pi in power of n over 2 of gamma of n over 2 plus 1. So what is actually this gamma function? This is actually a generalization of the factorial function. So in generally, it holds that gamma of z is exactly equal to z minus 1 in faculty. And this is exactly our measure of the unit n-dimensional ball. So let's take the simplest case ever we have. So for n equals 2, what we have here would be pi over 2 of gamma of 2, which is equal to 1 faculty. So what we get here is exactly pi. So exactly the perimeter, the measure of our two-dimensional circle. So moreover, also here, if the equality holds, then G is equivalent to a ball. So instead of a circle, what we have here is we were gonna have an n-dimensional ball or sphere in three-dimensional case, as we've seen before. So let's have a look at, first of all, the different preliminaries we have. So what we have here is we're having 3 basic ingredients of the isoperimetric theorem for n-dimensional space Rn. So we're having 3 ingredients, which is really fundamental for our proof. First of all, this is the measure m. Second of all, this is our perimeter p. And at the end, also the collection of our competing sets, which is the G's. So in our case, we are defining our M as the standard Lebesgue measure and P as the perimeter a la Di Giorgi. So this perimeter is named by the mathematician who actually proved this for the first time. And so let's have a look what is actually a Lebesgue measure. So intuitively speaking, a Lebesgue measure is the extension of volume of the so-called elementary sets. And what is actually elementary set? An elementary set is the finite disjoint union of intervals with volume. The volume of the union of our intervals ik is exactly equal to the sum of the volumes of ik. So the volume, if we're having a look at the interval together as a piece, a whole piece, the volume of that is exactly equal to if we're having summing up the little volumes of the little intervals together. This is not always true. It seems maybe a little bit, it should hold always. Nah, it's not always true. So that's the reason why we are having this restriction for our Lebesgue measure. So additionally, we have also, let's have a look at our perimeter a la Di Giorgi, P. This is defined actually with the Cacciopoli set C, and the definition of that, mathematically speaking, is the perimeter of G is exactly equal to the infimum of the limit of our perimeter of EK, where EK is just a sequence of smooth subsets of Rn, such that our measure of G with the symmetrical difference or with our EK tends to go to 0. It seems quite complicated, but I will elaborate on that a little bit later in my talk. But first of all, we can actually see Cacciopoli set as a set of a finite measure, and the boundary should be measurable, and this has at least locally, it should has a finite measure. So we call it sometimes also as a locally finite perimeter. So we can just think of it just as something which has a finite measure for today. So also we are having other restrictions which we will use. So the competing sets are bounded. So since the isoperimetric inequality is invariant under translation and dilations, the competing sets are all confined in some fixed ball. So what does that mean? We can just say we are having a competing set. We can restrict that in a fixed ball, which is big enough such that we can have it such that our competing set is fully contained in this ball. Okay? So we start first of all by considering only smooth sets only. In other words, what we're looking at, combining everything together, we're looking at the infimum of our perimeter of G under restriction that the measure of G is equal to M. I will elaborate on that in a second. And G is contained in a ball, which is exactly that. So it's all confined in some fixed ball. And G is smooth. So now a question coming up is, does the minimizing sequence have some convergence properties? So this is the first of all the question we would have a look at. And first of all, let's consider a minimizing sequence, which is GK, and K is equal to 1, 2, 3, and so on and so forth. And the measure of GK is exactly also equal to M. and our GK is also contained in some ball. And the most important thing here is our perimeter of our GK converges to P as K goes to infinity, and GK is smooth. So how is P defined? How is M defined? So let's have a look. P is exactly defined as our infimum of PK, and our measure of G is exactly equal to M, and G is contained in the ball, and G is smooth. This is exactly the set we've seen before, the restriction we have as the preliminaries, and our M here is exactly defined as our integral over Rn of the UK in absolute value, where UK of x is just the characteristic function, such that it is 1 if x is in our GK, and 0 if x is not in Rn, if it's not in GK. So what we have here is, with this M, it says nothing else than we are just looking at UK such that it is in our release set here. If it's not in our GK set, it's equal to 0. So we won't have a look at that. So additionally, we claim also that the support of UK is contained in a ball. What is the support of generally a function f? This is defined as if we're having x in a bigger set x, such that f of x is not equal to 0. So again, here we're just looking at things which is not 0. Everything else we will just leave it. And this should be contained in a ball. And our integral over our absolute value of UK of x plus h minus UK of x dx is smaller or equal to our h in absolute value times p of GK. What does that mean? So we can think of that, our UK of x plus h as a translation. So we're having the little movements around our x doesn't really matter. This would be bounded with something linear, which is in absolute value of h times some constant perimeter of GK. Okay? So now we use the compactness criterion for the Lebesgue space, which we have seen before as the restriction we use. And we deduce that there exists actually a subsequence of UK and an integrable function u such that our integral of Rn in our absolute value of UK minus u dx goes to 0 as k goes to infinity. So in conclusion, all of this summing up, what we have at the end is a sequence of subsets of Rn, Gk, and a measurable subset of Rn. G exists such that Gk satisfies the following. So this is exactly the restriction we've seen before with our measure and our balls, which is where Gk should be contained in. And our M of Gk in symmetrical difference with G tends to go to 0 as k goes to infinity. That means nothing else as, again, the translation doesn't really matter. That will tend to 0. So, therefore, the set of G fulfills actually the following properties, which we will use. So, first of all, the measure of G is equal to M. Measure of G without our ball is equal to 0. These two are quite intuitively self-explaining. And the last one is the trickier one, which is the measure of G plus H in symmetrical difference with G is equal to a Landau notation of something equal to H in absolute value. And where H is any vector from Rn, such that G plus H is actually just something like x in Rn, such that x minus H is in G. And recalling what is actually a symmetrical difference, this is exactly if we're having two sets, we are looking at the union without the intersection of that term. So this is, again, what we see here is little translations, doesn't really matter. It's already bounded by the Landau notation of something linear. And this here is actually also an alternative definition for our Cauchy-Pauli set we've seen before. So recall that Cauchy-Pauli set is just a set where we are having finite measures with a countable boundary. So now, since we are we've looked at the minimizer, let's have a look at the existence of the minimizer. So we have all those properties about convergence. We've seen that right now before. And now the question coming up is such a set G a minimizer? So is there actually a set which will fulfill all of those properties we've seen before? And now we can reformulate the problem as P of G, the parameter of G, is minimum under the following conditions, which is the measure of G is equal to M, measure of G without our ball is equal to 0, and G is a Cauchy polyset. So these three are exactly the conditions we've seen before. And here I've left out some properties of Cauchy polyset since the time doesn't allow me to elaborate on that too much. So for today, we will just say that by using properties of Cauchy polysets, how we've defined that, we can conclude that our perimeter of G is equal to P, where P is exactly defined as our infimum of our perimeter of G, where G is the subset of Rn satisfying our conditions 2.4. So this says nothing else as if there is a P of G, which is a minimum, then it must fulfill all of those three conditions. If not, that can't be a minimum. So now let's have a look at another essential part for our proof, which is the Steiner symmetrization. So what is that? So Steiner symmetrization has a wide range of applications. For us, in this case, we will use this to identify our minimizer. So far we've seen the convergence properties for a minimizer. We've shown that there is an existence of a minimizer. And now we have to identify our minimizer. So what is exactly our minimizer? For that, we will use our Steiner symmetrization. So what is the idea behind that? Let V be a hyperplane in Rn. So this is just a plane which is one dimension less than our n-dimensional space. So for example, if we're looking at something in three-dimensional space, a hyperplane which would be just a plane in two-dimensional space. So we're looking at that. Steiner symmetrization with respect to V converts any measurable set X of Rn into a subset Y of Rn through the following rules. So for every straight line L, which is orthogonal to our V, we will see if L has an empty intersection with X, L intersected with V is just empty. And if L does meet X, let L intersected with V be the following. So we're looking at three different cases. So first of all, if the intersection between L and X is 0, is positive or is infinite. So if it's 0, the point where L meets X it's just the point where L meets X. And if it's positive, it will be the segment of line L, whose midpoint is in V, and whose length equals to the one-dimensional measure of our L intersected with Y. And it will just be the whole line L if our intersection between L and X is equal to infinity. That might be complicated and we can't really imagine what's going on here. So let's have a look at the visualization of our Steiner symmetrization. So what we have here is, for example, we're having actually here a set. And with Steiner symmetrization, this line L would be exactly our V, and this is just orthogonal. So sorry, this is our L, and this would be our V, hyperplane. And what we have here is we are just actually looking at the lines, and we will just centralize that with our L. And if there is a hole, as we can see, we will sum up the length and centralize that such that we will have that the hole is not here anymore, so it's just outside here as a boundary. So as you can see, we're trying to deform that such that it's symmetrized around an axis and take out all the holes, it depends on how we are looking at the symmetrization, because it's also possible that instead of a horizontal, we can have a look at a vertical cut to have a Steiner symmetrization, so it depends. But the most important thing is we're trying to symmetrize that a set with our Steiner symmetrization. This is a very important tool for us. And let's have a look at the properties which we will use. So first of all, we have that gamma is symmetric about V, That means Steiner symmetrization establishes our symmetry. So as we've seen before, it will symmetrize everything, right? So second of all, the measure of x is equal to the measure of y. That means the Steiner symmetrization preserves our measure. And third property is that assume x is a Cauchy-Poly set, then y is also a Cauchy-Poly set. And our perimeter of x is bigger or equal to our perimeter of y. That means our Steiner symmetrization will reduce our perimeter, or at the most thing, or it's equal. So, and there are another two properties which is very important for our proof. What we have here is assume x is a Cauchy-Poly set and our measure is positive. What happens here is then either our perimeter of x is bigger as our perimeter of y, or x is just equivalent to a Cauchy-Poly set w, such that the intersection of y at w and any straight line orthogonal to v is either empty or a segment. We will have a look at later why this is that important for us, those properties, especially this one and the next one. So the next one says that assume x is convex. So here, this is an example of a convex set, how it looks like. And the measure of x is positive and finite. Then, again, either the perimeter of x is bigger or as our perimeter of y, or x is a translate of y. So what we have here with the last one, what we can see or deduce afterwards is actually for any convex figure, there is a sequence of Steiner symmetrization that makes it arbitrarily close actually to a ball. And there we are. We're right now using Steiner symmetrization. We will finally at the end land to such that if we're having a convex set, we can make it arbitrarily close to a ball. This is exactly actually our statement, so we will try to use that in our proof to prove that. So let's have a look at the identification of our minimizer. So with the Steiner symmetrization, we've seen already, this is actually something we can use to identify our minimizer, and this should be equivalent to a ball since of the convexity I've said before. So the statement here is let G be a minimizing set, and we claim that G is equivalent to a ball. And how we do that? We are considering any hyperplane V passing through the center of a ball. And consider the Steiner symmetrization of G with respect to V, which is defined as L. So by properties of Steiner symmetrization, so here we will use all 5 properties we've seen before. So first of all, the measure of L is equal to measure of G, while L is contained in a ball. Thus, L is a competing set. Second of all, since G is a minimizer, we must have P of G, the perimeter of G, is equal to the perimeter of L. So what that means, so we've seen before, it could be that it's bigger or equal to our Y in that and before. And in our case here, G is a minimizer, so the equality holds, okay? So G is equivalent to a Cauchy-Poly set where the intersection with any straight line orthogonal to V is either empty or a segment. Using this property, we can use that, and since V is also arbitrary, what we will get we will conclude that G is exactly a convex set. So now here we are using Steiner symmetrization. We will conclude that since G is a Cauchy-Poly set, we'll conclude that we are having actually at the end a convex set. And if we're having a convex set, what can we do? We know with the last property that with the Steiner symmetrization, G must be equivalent to a ball because using Steiner symmetrization, we can approximate it arbitrarily close to a ball. Okay, so this is actually already the brief idea of the proof. Let's sum it up. So what we are doing is in our first step, we have to show that there is actually a minimizing sequence where G is contained in a ball for the problem that the infimum of our perimeter of G, where G is contained in a ball and our ln of g is equal to 1. And step 2, what we've seen is if g is a minimizer, then g must be equivalent to a ball. So what that means that our minimum of our perimeter of g, where g is contained in our ball and ln of g is equal to 1, must be equal to our measure, which is n of omega n in power of 1 over n of our measure of g in power of n minus 1 over n. So here there is actually also some calculations we need to do, which I want to elaborate here. And step 3, the last step, is we have to distinguish between different cases. So for today, what we've seen is the case if we are having a bounded set. So P of G is, so if it's bounded. So we're taking any measurable set G with ln of G is equal to 1. If G is bounded, then G is contained in some convenient ball. And therefore, we can repeat our step 2. Since we know the minimizer is, we know that there must be a bigger or equal here. Since it's not the minimizer, so then it's just something which should be contained in a ball. Okay? And now let's have a quick look in case. So we deduce from step 2 that P of G is bigger or equal to our measure here, and that if equality holds, then G is equivalent to a ball. And in case of an unbounded set, we are having two options. So the first one is if the perimeter of G is infinite. And here, this is just a trivial case. And for the second one is if our perimeter of G is finite. So what we are going to do, which I didn't show here, is we will use actually an approximation theorem, which would allow us just to repeat our steps from 2 and 3. From 2 to show the inequality. Okay, so this is actually the 3 cases which we should distinguish if we're showing something in this case in n-dimensional case. So we're turning slowly to our end of my talk. So we will have a look at some applications. So at the beginning, we've seen an application in mathematical physics about the spheres. And now let's have a look at an application in geometry and analysis. So what we have here is we're looking at a conformal mapping of a double connected domains. So as an example, I would like to show you a briefly proof sketch, a sketch of a proof of our theorem, which is consider the family of all doubly connected plane domains bounded by an outer curve C1, which is this one, and an inner curve C0. For each domain D, let AI be an area bounded by Ci, which I is equal to 0 and 1. Then, among all domains conformally equivalent to a given one, the minimum of A1 over A2 is attained by a circular annulus. So it seems quite complicated, this theorem, but if we're seeing the sketch of the proof, it's actually quite easy. What we're doing is the following. So the idea here is exactly we have to use the isoperimetric inequalities. So before that, the mathematicians used to prove that with Laurent expansions, which is much complicated. And with the isoperimetric inequality, we can simplify everything. So what we have here is let R0 be smaller than our C in absolute value, smaller than our R1. So this is actually our R1. And this smaller circle here is actually our R0. Be a given annulus, and D is its image under a conformal mapping F of C. So what we have here is let LR be the length of the image of where the absolute value of C is equal to R, and AR is exactly the area enclosed. So first of all, what we are going to do is we are just using the isoperimetric inequality in the plane here. And afterwards, with some calculations, if we're just integrating over the area, we will get, or we can estimate it as 2 pi over A prime of R. Therefore, what we get is by rearranging this inequality, we will get that 2 over r is smaller or equal to a prime over ar, where r is between r0 and r1. And finally, the only thing we have to do is we have to integrate the whole thing from r0 to r1. So this is actually a little bit similar as in physics, how you integrate that in physics 1 and 2. What we have is afterwards that PR1 squared over PR0 squared is smaller or equal to A1 over A0. And this is exactly the statement we should prove. And as you can see with our isoperimetric inequality, it's way faster than if we would use a Laurent expansion. So now we're already at the end of my talk. Thank you for coming, and I hope you enjoy that and could understand a little bit the concepts behind the isoperimetric inequalities in the two-dimensional space and as well as in the n-dimensional space. And have a lovely day, all of you. Thank you.
Yeah, so thanks for the talk. It was very informative, I think. So the apéro is happening now in G69, and next week Han Miru is going to be talking about category theory, so categories, and I think that's also going to be super interesting. So come by next week for the last talk of the semester, and then we're back in the fall. All right, thanks.